Okay, so this week we're going to go chapter 9. So chapter 9 is about calibration of your instruments. So calibration is the measurement of, again, accuracy. We're trying to measure your own instrument with a standard and to see if your instrument is measuring according to that standard, okay, giving you the correct measurement. Because the standards usually are the correct measurement, we assume it and we also check it with greater or grand standard or master standards. So ensuring accuracy is the function of calibration, okay, to make sure your instrument is accurately measuring so that you can use your instrument continuously. And each calibration steps, and they depend on many factors. So at each step, all the factors contribute error, and that distorts your accuracy. Not a lot, just a little bit. So only the inherent accuracy carries the accuracy forward. So here you can see the steps. So when you look at it, you can trace the step all the way back to the standard, okay? So that's where your instrument or your measurement was produced. So here when you look at carefully, you're going to go precision, accuracy, functional feature, observer, environment, and go all the way back. Inspection of depth, and then gauge, lab, metrology lab, and then you have NIST lab, and then your international standard. So this is how your measurement or your instrument, okay, the root is right there. Okay, this is your calibration rule 10.1, and it's a pragmatic rule. It's not a law, and it's totally based on your practical result. So the rule is telling you the instrument that you're using got to be dividing the tolerance into 10 parts, okay? So the purpose of this rule is to eliminate 99% of the instrumentation errors. And of course, for the previous step in the measurement. So when we always apply this rule to every step in the measurement sequence until we get to the point that you can measure anymore with this instrument. And then the results are you get fewer bad parts, okay, accepted, and good parts rejected. You should read fewer here too. So fewer good parts rejected, okay. And instrument definitely includes the standards. So here you can see your work tolerance got to be between here and here. So that's your plus and then a minus, and this is your range. And this rule is telling you your instrument got to be dividing that tolerance into 10 parts, or it's not good for calibration. And then your snap gauge tolerance here and your gauge block tolerance here. It doesn't matter which tolerance, okay? If your instrument is again dividing the tolerance of your instrument into 10 parts, you are okay with this rule. And this rule 10.1 demands 1000 times the precision of the actual part, which exceeds present measuring instruments. So NIST is currently investigating 1 by 10 million measurements. That is really, really small and finer, okay? They're trying to increase their standard. So limitation in, of course, the NIST, they do all of this measurement or in the national lab. And limitation of 10-to-1 rule. And here you can see the very first one is 0.001. The comparator is plus or minus 0.0001, okay? It's getting smaller. And then the setting gauge getting even smaller. Calibration comparator smaller. And the master standard is even smaller. So the smaller units is telling you that we can measure up to that small, okay? So therefore they're powerful standard. So if your part is here, you calibrate with this. You can also calibrate your instrument with this. We calibrate this instrument with that and this and that. So that's how you trace all the way back to the original standard. Okay, traceability. and your 10-to-1 rule. Here is your part. We use gauge to calibrate the part. We use a setting master to calibrate the gauge. We use a calibration instrument to calibrate the setting master, and then the plan's master standard to calibrate the calibration instrument. And the master standard is calibrated by NIST standard, which is calibrated by your international standard. So this is your controlling unit. And we do this again, okay, all the way back. So the discrimination requirement arises with the part tolerance and extend back all the way to your root, which is your international standard. Accuracy arises at the root, which is your international standard, then progresses through each calibration step to the part. Okay, so this is our calibration procedure, and that is happening behind the scene, and you are right here. So traceability is the procedure for determining that none of the connecting links between the part and your NIST for the United States has been severed. And it is required by law on government contracts and by sound economics for all other measurements. You have to do it, okay? Without that, everything that you're doing at your company, it wouldn't be legal. Accuracy is derived again from a standard, and if the standard is not accurate, we cannot measure accurately, even if we follow the 10-to-1 rule, okay? So here's the role of error. Error, large or small, they always present in a measurement. There isn't a measurement without error. So this is because the active measurement alters the item being measured in the measurement system, so we never know a true measurement value, okay? But we do everything we can to be as close as possible. The closer your data is to your measurement true value, the better your accuracy is. So metrological assumption is that we do not know everything about the standard, so therefore there is always error in our knowledge. So classification of measurement errors are listed right here in this table. So the first one is systematic or fixed error. So in this error we have 4 parts. So that's your calibration, your human, your technique, and your experimental. So these are all types of error in a systematic or fixed error. So frequency systematic is usually periodic, okay, and location, instrument, observer, or technique. So meaning like you are using an instrument, and when you read the reading, you're gonna make a mistake. When you do your measurement technique, you're gonna make a mistake, because that's how you get this systematic error, and the causes malfunction, okay, repeated malfunction of one or more elements. Detection, we find these errors by comparing your measurement or substituting it. So the very first of your systematic error is your calibration. Frequency again changes with measurement. Location is happening in your instrument because it's calibration. Your causes your false element design and construction error. Your detection is your comparison to superior standard. And you can fix it by replacing the instrument, okay? Because your instrument isn't good, so you can't do your calibration correctly. Error prevention is your instrument evaluation by checking your instrument all the time by calibrating it. And I'm not going to read everything for you here, okay? So I want you to read each type of error under your systematic error and try to know the frequency, location, cause, detection, remedy, and prevention. Second error is your random or accidental. This is out of your control because it's an accident. It is a random error in your instrument, observer, technique, or part, okay? And it's happening erratic malfunction of one or more elements or part. You can fix it by comparison or substitution. And there are three types of random error: your judgment, your condition, and then your definition. Okay. And again, try to get all of this, and they're gonna be on your test. Illegitimate error, there are three types of it. So illegitimate error is happening like random, sometimes periodic, and sometimes continuous. And you have your instrument or observer, okay? Then you have your outside inference or other completely avoidable disturbances. It causes the error. You can fix it by reappraisal of procedure. You do the same thing, and please study A, B, and C, the types of your error, and then causes, okay, and then how to fix it. Discrepancy is nothing but it is just an amount, okay, by which the results disagreed in repeated measures. So one person is going to do a measurement and you're going to do the measurement. You're going to do the measurement 2 times and you're going to see there's a disagreement, meaning that they're not the same. So therefore you have a discrepancy. Random error, again, because of this, okay, discrepancy. So meaning like your measurements are not the same. Your measurements is not the same with someone else's measurement. So you have discrepancy. So the cause of discrepancy is your random error. And that is totally a part of every measurement. Systematic error is a uniform error from which all readings vary. This is also another part of your measurement. So every time you do a measurement, you have 2 errors happening at the same time. The very first one is random and the second one is your systematic. And you can't avoid any of that error, but you can make it smaller, okay? Why? It's because we are living again in the world that is always changing. You yourself is changing every second of the time, even the smaller amount of time, okay? The environment is always changing every second of the time, so therefore what you're measuring is also subjected to these changes, even if we think like they're not changing, but they do. And those kind of changes definitely affect small measurements, okay? And that is completely displaying instruments like that, sensitive instrument like that, so therefore we have to be very careful. So very serious measurement, we usually do it in a laboratory, okay, to get as accurate as possible and to reduce these errors. In the lab, it's erroneous error, but we're not looking for it to reduce the error there. You're just learning what type of instruments they are and how do you measure it, okay, just the basics. So that's fine to use a very old instruments in the lab. We don't need it for now for accuracy. But if you want to enter the career in metrology, then you definitely need to have a very stable hand and a good vision and a very patient mind, okay? And you can be able to be in this type of career and be very successful with it. Also, they pay a lot of money. Okay, determinate errors, error that you can evaluate with any logical process. So those type of errors are something that you can be able to understand by looking at with a logic. So indeterminate error are something crazy that you cannot evaluate with any logical process. Illegitimate error is not legitimate, not valid at all. So this type of error should not exist at all. Okay. Interaction error. So we have many different errors that are happening in the measurement, and they do interact. Okay, so errors have effects on each other. People living there and each person have effect on the other person, even if you don't know each other. Just like that, errors are happening in the measurement system and they do affect each other. So errors are classified as dependent error, independent error, and correlated error. So here you can see each type is listed nicely right here in this picture. So errors interact to produce accurate results, and we must know the error and the interactions to assure, again, reliability of these results. Okay, if you don't know the error, if you don't know what they're doing to each other, you cannot be able to assure your reliability. So every time we try to fix something, we definitely need to know the problems. If you don't know the problems, you have no way to fix anything. Okay, So here, type of error in area measurement. The very first one is dependent. Micrometer error. Example is the result is no way error can cancel in area computation. Observational error. Independent is your observational error type. Result is your errors may cancel out or contribute. Correlated error, your surface finish error. Your error may compensate other errors. Okay, those are your interactions telling you what this error can do to others, but is constant for any one value. So here they are your interactions. These are the type of errors. So here the problem is determine area A. So a little block right here, that's your example. Your variable, so you have your micrometer error. Second is your observation error, okay? And then you have your surface finish error. So dependent is here, independent error is here, and then your correlated error is happening on the surface, okay? You can do the measurement lengthwise. You can also measure this little block the widthwise, okay? Doesn't matter how you measure, you always have a mixture of these three errors there, okay? And when they interact to each other, we call that interaction of errors. This is just a cartoon, okay, showing you, and here you can see his name is written on his lab coat. I have a similar one. I'm going to bring it over to the lab and show you, and the gloves we have to wear it. So dependent errors is the errors that cannot be cancelled out or compensate for each other. So those types are called dependent. Independent errors are the errors made when the person making the computations has no way of knowing when the results are correct and when they are not. Computations is making a just measurement. So correlated errors, your surface error in the previous example, so the errors caused by systematic relationship between independent and dependent errors, okay? This one and that one. So when they make a systematic relationship, you get correlated errors that happening on the surface of the object or the part you're measuring. Basic calibration procedure. So what's the procedure to calibrate? So calibration consists of 3 steps, okay? So the very first one, you're going to determine the variable that might contribute to measurement uncertainty. Second, you're going to measure the error contributed by each variable. So here we get the variable. Second, we get the error for each variable. And then the third, you're going to determine the net effect of the interaction of the variables on the instrument's measurement capability. Okay. So there are 3 steps in calibration procedure. Okay, uncertainty of the instrument is made up of all the composite errors from each of the instrument's separate characteristics. So that's your uncertainty. It is uncertain, okay? That's why you have all the errors. And this is actually from each of the instrument's separate characteristics. So your instrument have parts, and these parts have characteristics, and they're going to produce different errors. And the composite errors is going to give you your instrument the uncertainty. Okay, so variable is each possible source of error. Calibration standard is your general instrument calibration procedure and is totally covered by our ISO standard. The number is 10012. You can become certified ISO as well, okay? And you do consultation in metrology as well. So before each calibration, we run calibration checklist in figure 9.7. So this one, after these steps, the instrument is ready for calibration. So before we actually do the calibration, we check these things, okay? Pre-calibration checklist. So A is your identification. So very first one is, does the information accompanying the instrument Agree with the serial number and or description of the instrument. Do you have the record of past calibration? Do you have the manual? Do you have all applicable federal specifications? Do you have a report from the user concerning real or imaginary troubles with the instrument? Do you have instructions for disposing of the instrument after calibration? Okay, so these are everything that you have to know before you ever go into the calibration. So people in quality assurance, quality control, and quality system like us, we usually have to do calibration. Okay, so it's nothing but checking. So quality people gotta do a lot of checking on other people and their job. Okay, so in order for us to be able to check something, we have to have all the manual, all the standards, all the specification in hand before you ever get into the checking of the procedure or the instrument. So in this case, in instrument checking is calibrating it. So here we're going to check if we have all of that. And usually the operator or the person who is using the instrument is always going to give you some reason, okay, why they need that instrument to be calibrated again. So they'll give you all kinds of troubles that they're getting with that instrument. Will ask you always to get a new one, okay, but your job is to save the instrument, save the cost, and calibrate it back to its own standard, okay. Okay, so the next pre-calibration check is requirements. So here what we're doing is checking is the environment for the calibration suitable for the precision expected. So you check your temperature, humidity, the people around there, okay, have the draft, temperature change, vibration, interference, check everything. Your lab got to be super clean and it's without dirt is better for calibration. We also check our, suitable standards if we have the standards on hand, and if the standards have already been calibrated. If you're going to calibrate with a standard that have never been touched for like a year, it's no good. So all the necessary calibration instruments and accessories on hand. Do we have all of this? And are they in calibration? Check if they already calibrated. Okay. Is a heat sink or adequate capacity on hand? Do we have the heat sink? Sometimes you need it in order to balance your instruments in calibration. We're going to check if we have the necessary supplies. We're going to check if we have paper, pencil, okay? We're going to check if we have the necessary packaging materials. So these are all your requirements. It's not limited, okay, from 1 to 7. You might have something more. It depends on your lab and depends on what you're checking or measuring. Preparation. So preparation, we're going to check it again, have the instrument, the standard, and the calibration instruments be normalized. So you check if they have been normalized. We're going to check the instrument, okay? You're going to check it visually, so that's a visual inspection. And have the references and contact surfaces been inspected from damage, wear, and alignment. So make sure all your surfaces are good to go. So these are all your pre-calibration checklists. Okay, so calibration, what are we doing? We calibrate an instrument that is not needed to be calibrated to a standard that is the same size, the shape, and the material as the part the instrument is measuring. Okay, we're calibrating the instrument. You're using the instrument to measure a part. We are using an instrument and calibrate it so that the instrument is going to give you a correct measurement, and we use another standard, okay, already calibrated standard to check the instrument you will be using to measure your part. Okay, so there are 3 objects in it. One is your gram standard or master standard. Second is your instrument to be calibrated. And the third is your part. Okay, total error is the sum of many separate errors. So errors can add up to one total for one reading and a completely different total for a different reading. Again, even if we're reading the same thing, they're not the same reading. They're different reading. Why is it different? Because you are different. And then the environment is different. We're always different every second of the time. The environment is different again every second of the time. So therefore, what you measure the same measurement a second ago, and what you measure the same measurement now is not the same. Okay, so therefore we always have the total error. Calibration of the vernier caliper. Okay, your instrument is vernier caliper, and we're going to calibrate this. How do we do that? So vernier caliper, we're going to compare that, okay, to A standard, your master standard. And we're going to compare at every point. So we usually use a gauge block, okay, as a standard of calibration. So when we start our lab series, we're going to start from calibration. And we're going to use our gauge block, okay, the one that you pick out for 5 gauge blocks. I asked you to pick it out, okay. So those are going to be to your standard, and you will be totally calibrating your vernier, okay. And then use that one after calibration, and then measure, and then check, compare your error before the calibration and after the calibration. Okay, so for example, 300mm vernier caliper with a discrimination of 0.01mm and a range of 300mm, we got to take, okay, we must make 30,000 separate calibration measurements. And this is what we call compared to a standard at every point. It's a very tedious, okay, job to do calibration, so therefore you need to have a very patient, okay, very patient mind. So if you want to save time, you can skip it. And you can do selective checking at multiples of 10mm. Okay, so right here, but they could come with hidden errors. Okay, no, this is wrong. I gotta change that one. Anyway, so but they could come with hidden errors. So skipping, okay, a lot of the checkpoints is not a good idea. But in a company, again, the small businesses, medium-sized businesses, and the regular company, they do not care. Okay, they just don't care, and they just go with the error anyway. So therefore, if you think about a development of a drug, okay, or your medicine or tablets or whatever, and they always come with a 65% acceptable range. That's 100 minus 65, a lot of error in it. Okay, so therefore you will always have side effects for every pill that you are swallowing. Okay, so always come with the side effects, and that's because of the metrology. Okay, when they develop that product, they don't really care about this accuracy and precision. Okay, so that's CIA and FBI have been doing. Okay, FBI in the United States, CIA in the international businesses. So that's their work to check if they are following the standards or not, because the consumer products are used by the people, okay, billions and billions of people all over the world, and they're making money out of you by giving you very low standard products. So the serious product includes your food and then your drugs, okay, medicines that you buy, and majority of the people cannot be able to afford the doctor, so therefore they use over-the-counter pills, okay, and a lot of the flaws are right in there. So FDA in the United States, they don't care. They only want money for your patent to pass, okay, to give you approval. So therefore, in the end, always people gotta suffer. The FBI and CIA job is not always trying to follow the crime or criminal, okay. There are many crimes that are happening on the paper, so that's go into the policy, checking the standards. And metrology, crime in metrology is your consumer products. So why that is happening is because of these errors. Okay, they do not follow what they're supposed to be following and skipping the calibration to the standard. They don't hire scientists or metrologists, and they just ask anybody and they're working there by telling them experience matter. But these guys, no matter how many years they're working, if they are not trained to do a precision work, they just don't know. And most of the time, they do not care. And you will be one of them as well, okay? And you will know when you get into the work. That's because you're tired, probably tired, so people don't want to work in a right way. Okay, I would say right here in the right way, and they also think it doesn't matter. Okay, that makes a lot of issue in the world. That makes why a lot of the products are below the average standard. Okay, it's not even at the average standard. So there are a lot of issues going on in there. In quality department, as you go up, you have to read all these issues, okay, how to solve them. Okay, next one. Now we're going to visualize the errors by using a graph. So every time we're trying to visualize what is happening, okay, in the data, we usually throw the data and then graph it so that we can be able to see the trends, meaning like how are they going, are they increasing or decreasing, are they staying in plateau, or are they curving, okay, are they growing linearly or exponentially, or are they reducing? So that's what we're looking at in the graph so that we can be able to predict the future. Okay, so to visualize the errors, we graph them. So here in figure 9, you can see types of uncertainty that the instrument may have from these graphs. So here you have your true values that we don't know, and then our readings that we try to do as close as possible to true value. So your typical deviations is your errors, and your errors come from your perfection, deviation from your perfection. So this is just assumption of a perfect instrument. And these are your data, so your readings. Okay, so true value right here is higher than your reading. Now the true value lower than your reading. And then calibration points are right there on the reading. Okay. So if you have like a calibration point in this graph, you have 4 of them, and that is totally on the line of reading. So therefore, your instrument is kind of okay, I guess. So here we have our 0 settings, and then we take the data, your true values, on the y-axis, and then your readings on the x-axis. The result of 0 setting error. So now the error, you can see it that way. So the actual instrument line is right there, and this is our perfect instrument. Okay. So here all of your data are right there. So definitely not in line, so therefore you have 0 setting error. Okay. So if you pay attention to 2 graph, you're gonna see here this perfect line, okay, perfect instrument line is interacting with your data points. Okay, your data points right there. True values. And this is your reading. Here is your perfect instrument line. This is called topical error. Then you can see how it curved out. Okay, so here, okay, okay, not okay, not okay, going back. So those are called the topical errors, and they're frequently caused by, again, instrumental wear because your instrument get old. Now the next one, true value, and then you have your readings, and it's going like a little S, okay, curve. So here your data are not on the instruments, only one of them is slightly on the line. So this curve is either result from the main scale error, okay, the beam, or your vernier scale error right there. Variables to be calibrated. So variables, they produce errors, therefore we have to calibrate the variables as well. So first we find variables that may contain errors before we determine the readings we need in calibration, okay? So what is it telling you is first you're going to look for your variables, and these variables usually give you errors. And you're going to do that looking for the variables before, okay, you determine the readings that you need in your calibrations. So if you don't do it, you have more, okay, errors from the variables as well in your total error. So you have your functional, and then you have your metrological. So here is your instrument. These are your jaw skin, your fixed one, and then here is your first reading, okay, your main scale is right there. So here is showing you main scale accuracy between the jaws, okay. This is your beam, and the main scale is written on the beam. And then you have your vernier scale inside of it, your review, okay, amplification and discrimination. So graduations are right in there that you can be able to read. So instrument variables are here, wear, scratches, birds on reference surfaces, 0 setting that is happening between this area. happening right here between the jaws, your main scale error. And then your vernier scale amplification and discrimination can also produce error. And then where an adjustment of mechanical action can, because every time an instrument is taking an operation, you are wearing these parts out by rubbing to each other right there. Clarity of your graduation again here. This is just a previous location or position, and this is your new location, so they draw it with the little lines right there. He is just an NIMT metrologist inside of the quantum technology lab. So you gotta weigh like that in order to reduce the dirt. Okay, so we found 4 variables generally, okay? 2 of them is metrological and 2 of them is functional. And that is for a vernier caliper. So we've got metrological, the main scale, metrological, the vernier scale, functional, the mechanical action. Another functional is a condition of the contact faces or jaws. So here is another graph, your linear uncertainty and accuracy, okay? So uncertainty is the measure of accuracy, okay? So uncertainty of an instrument is the maximum, again, error that it may add to a reading. So uncertainty is the measure of accuracy. So here we're going to see no linearity error. Uncertainty is maximum error where it happens, and this periodic error repeats throughout the range, okay? Happening throughout the range. Linearity error only in this case, and you can see the function, okay, this one, that is that one. So function of length uncertainty remains maximum error, but only pertains to maximum length, okay. The next one is your periodic error and linearity error may reinforce or they may cancel out each other, okay. Uncertainty remains maximum error wherever it happens, okay. Uncertainty and uncertainty is your maximum error, okay. It's always that because it is your measure of accuracy. As long as you're measuring, you've got uncertainty, even if you don't have linearity error, even if you have only linearity error, even if you have periodic and linearity error and they may cancel out, you still have uncertainty at maximum, okay. So if you know about that, it's all right. Okay, so remember when we use the vernier in that chapter, if you read the handout, you understand. If you don't, I don't know. You have to read your handout and study. Studying is not just coming to the lecture and listen to it. You won't get anything out of it. Okay, you got to come to the lecture and listen. You have to participate in an in-class activity. Okay, even that your knowledge is only about 20%. You have to go back home, sit down, and read the handout. Reading is so important for studying. And then you gotta read it again. And then you're gonna read the key points, okay, in your PowerPoint. And then you're gonna listen to my lecture. Now I'm putting it in video for you so you can listen anytime you want, whenever you're free, not limited to only in class. And you have to write it down, draw the picture, okay, draw the flow chart, and try to take out what you read inside of your head back in or onto the paper. Okay, that's what you have to do. And that process, listen, read, write, listen, read, write, retain it in your brain, take it back out, is the process of study. And you have to do that again and again and again and again and again and again before you come into the exam or before you ever try to get a job. Okay, otherwise you're going to be doing all kinds of crap, at your job and hurting like other people indirectly without you even knowing it. Okay, so remember to centralize the caliper carefully to duplicate the normal field in vernier calibration to a gauge block. Okay, so here we have 1, 2, 3 gauge blocks we use, okay, as a standard. So this is a very long gauge block, and we are calibrating a vernier caliper in this example. Okay, measuring and gauge block has already been calibrated. We assume that. So your vernier got to give you the exact measure of this length of your gauge blocks. Okay, if not, then your vernier is not very good. Okay, it has error in it. Below is a table. So here you have table for true values, and you have another column for observed value. Okay, so when you look at it, the true value is this, and after you calibrate it, you observe these values in your instrument. So you can see it's a little bit off. This 2 points seems to be quite good. Okay, that 2 is off, 0.003 off, and here 0.001 off. Okay. Hey, meet the metrologist. This guy name is Ron. Okay. Well, this is anyway life of a metrologist doing nothing but measuring, trying to calibrate, trying to make sure the instrument is working in the way it's supposed to be working. Calibration of coming into micrometers. So for micrometer, we're going to take a look at the pitch, okay, the axial, and then your lead is your rotational distances. So here your pitch distance between 1 point on one thread, okay, on one thread, and then the same point on the next thread is your pitch. And your lead is the amount of movement between the male and female threads for one revolution. Your pitch is your axial and your lead is your rotational. Okay, there are two, again, variables, so therefore they can produce errors in measurement. In a screw thread standard, so they may be plus or minus and are independent. Okay. Here in this picture, you can see your axial and your rotational thread errors. And these error types are again independent errors, so therefore they can affect the micrometer accuracy. And we call that, you don't need to know this one, just a common word, drunken thread, okay, because it's not producing the right accuracy because you have errors in your axial and rotational thread. So here, true advancement per degree of rotation. In your graph, you're going to see like this. So actual advancement due to errors is going that way, okay? And then you have a little go up and down errors right there. So your pitch might be uniform, okay? So you can never be able to judge with your own eyes. So there may be unequal advancement during part of the rotation. So every time you will operate the micrometer, you will always have a little bit of unbalance in there, okay? And they're all unequal. It's always happened that because it depends on the hand of the person who is touching it as well, okay? Because the force is, they're different. So different forces are subjected to the same instrument, so therefore you have different errors. Observational variable in calibration. Observational variable. So right here, we're still in micrometer. So for micrometer, we remember the field, the torque variable, okay? It's a very significant effect on calibration. Again, it is another independent error. So other observational variables are your parallax and your biasness, okay? Writing the data that isn't true is called biasness. Kind of like a lie right there. Parallax is your error in your vision, okay? Sometimes you're going to have both of them. Because you have a vision error, but you don't want to confess you have it, and you want to stand your point that you're correct. So you go into biasness, okay? So don't, if you want to be safe, you never say that you are correct, because there really is nothing that is correct in any of the scientific endeavors, okay? We have only closeness, or how close we are to the true or absolute, okay, whatever we're studying. So if you try to claim that you're perfect and your measurement is the measurement, then everybody know that's not right, okay? You're not a real scientist, you're just a fake, or it's not good, okay? So don't do that. So you always say, like, to save yourself, you always be humble and say that your measurements are your best, and okay, it is as close as to your true data, and that's about it. So, and always confess that vision is not that good, and you may be biased. Okay, you can't say that I am free of bias. That cannot be true, because we do not own our own consciousness either. So sometimes, okay, you may be committed on biasness in your data. So therefore, we try not to. Therefore, do not say black or white for anything. Okay, try to stay out of it, or in between. Okay, balance is so important. So anyway, here it shows your micrometer calibration position. So here you're gonna go the first position at 0.008, second position at 0.195, and the third one is 0.390, and so on. So this is one of many sequences, okay, of your position of your calibration positions in your micrometer, and it's checking both the pitch, again your axial, and then your lead is your rotational variables, okay. Okay, so internal instrument calibration, those that we use to measure internal measurements, we use the internal instrument. So how do we do calibration for the internal instrument? So it's the same calibration principles that we follow for external ones, okay? So in calibration, we use specialized instruments, okay? So sometimes you have to use a floating table like that, okay, is one of them. It allows you align the line of measurement, okay. So in this case, is using a ring gauge right there, okay, precisely with the measurement axis of the instrument in calibration. So that's because for internet instrument, you need to have a very stable hand, and just like yeah, you need to have a stable hand. So therefore, if you don't have a stable hand, we usually don't, okay, because we're tired. Humans are tired, stressed out, and because of that, you won't have a stable hand. So therefore, when we do the internal instrument, we usually use a amplification or support, okay. So that's your amplification for your calibration, which is a support. So that's a floating table here, and here you can see your ring gauge, and then this is just a roller part of this table. So basically, trying to tell you, this floating table, okay, of the internal comparator minimizes your friction, okay, one variable that is going to impair aligning the gauge with the axis of the instrument. So all about reducing the errors coming out from the friction, which is a variable, okay, to mess up with your alignment. So here you can see the floating table in real life. They're usually shiny in the calibration lab, okay, because they usually polish everything and clean the surface all the time in order for them to be able to get the correct or accurate calibration. Okay, working standards. Working standards are nothing but your standards that are working, and we're going to calibrate that. So what are we doing there? In working standards, we call them gauges, and we have 2 gauge boxes in our lab. They're pretty messed up, but it's okay. Okay, for education purposes, it's alright. For real lab, it's not alright. You always have to buy the most expensive and accurate one. Used to set or calibrate all the gauges, and also used for extremely precise work. Okay, so they are calibrated with, again, your master standard. The master standards are calibrated by your grand master standards, and your grand master by NIST, and then your international standards. Anyways, zero set the instrument. So first, that's what you have to do. Zero set it, okay, to the gauge blocks, and measure the working standard to the same degree of precision to that gauge block. So you already know. So if I ask you, what are we doing in calibration, you should be able to know you're using a standard, and you are trying to check your instrument is still functioning and giving you the correct measurement, okay, of that standard. So therefore, you can use it to measure other parts, okay. So calibration of master standards and traceability. So we use a grandmaster again, and the best ones are your light waves. Light waves are nothing but it's just an instrument and we use the waves to measure, okay, from this point to that point. So if you do the wave, it's very, very precise because it's really fast, okay. Of course, we use the live wave instruments in order for us to be able to catch that distance, and it's digitalized, so it's going to come up in a screen that you can just read it. So to calibrate master standards in the calibration labs, again, we use the light waves because it's very accurate. Okay? And the calibration is so important in, again, manufacturing facilities because we're producing billions and billions and billions of products, billions and billions and billions of different products, okay, all over the world. Whatever you're touching in your room comes from manufacturing. Whatever you're wearing comes from manufacturing. Whatever you like in the refrigerator comes from manufacturing, and they're all measured by the metrologist. Okay, so this is the one area in industrial technology that most people don't go in for as a career because it's kind of hidden, because it's linked to our line, which we call that quality, okay, quality system. So quality control, quality assurance, quality tech, and quality system do this job. Okay, metrology is a part of that career. So therefore, you might want to get into quality group. You usually get a supervisor position in quality group, and also there are many certifications that you have to complete. So I think a lot of the students, they back out because they don't want to study more than a degree. So that's what usually happens. But for quality, you have to keep going. You have to keep going all the way to your terminal degree for you to be able to land in one of the labs like that. Okay. So calibration is so important in a manufacturing facility, again, because it has become a legal system right now. Okay, you have to follow the standards. Everything got to be within the ISO, we call it, okay, ISO, and people are going to come and check in your company if you are following these standards, okay. And those companies who don't follow ISO usually get into trouble with your FBI, the international American international company, will get into problem with the CIA. Okay, so the usually CEOs and owners usually get into lawsuits for not following the standard. So make sure you don't save money for following the rules. Just pay money, okay, to the government and stay out of trouble. That will save you a lot in the longer run. So record and correct calibration reading. So here we have, it's a good practice to systematically record and correct all readings, okay, from rounding off errors or any other errors. So readings are usually you round off in the wrong way, okay, so make sure you follow your round off rules, okay. And rounding off calibration results, unnecessary decimal should be totally round off. Gotta get rid of it. We don't need it. So you don't want to carry a long, okay, decimal list right there. You will get rid of and keep only what you need. You can go for significant figures is usually the average, value that we use. Some company might go like 2 significant figures. So it depends on your company again, or depends on what you are measuring. We're gonna go that way. So we use conservative and liberal methods to do that, and this is your actual reading. This is your conservative rounding off method, and here is your liberal rounding off method. Okay, so both methods, they manipulate the wear in the instrument. So here actual reading is giving you blah blah blah. So here is your conservative rounding off. I'm going to assume that the wear exists in this standard, and then use a rounding off interval to reduce the standard. Okay, so hence the gauge calibration now we get is 1, 2, 3, okay, instead of 4. So here 1, 2, 3, 4, and then you have 1, 2, 3, and I'll have 1 at the end, and we're now rounding it off. Okay, so we go only up to 3 sig figs right there, and here you become 0. Okay, so we don't know if this is going to be 4 sig fig or a 3 sig fig, so it depends on what you have here, but right now it's 0, so therefore it's 3 significant figures. So liberal rounding off is, we're going to keep it just right there, okay? So rounding off up to 4 significant figures, okay? Conservative, we're going to round off to 3 significant figures. and put in 0, okay, for the fourth, okay. So like we're taking this for the conservative and we're taking that for the liberal, rounding off, okay. This is not a political thing. Actually, the history says it's based on the nature of the conservative and the nature of the liberal, because the liberal usually give you more and the conservative just cut you up. So therefore the conservatives, you get 0 right there, and the liberal you have 1 right here, okay. That's just a joke. Okay, the last one. So here's a liberal runoff. So this runoff affects the conclusion in calibration. So definitely, because there's 1 at the end, and the conservative runoff is ensure even greater separation from your observational error. Why? Because you're cutting the last significant figure out. Okay, so therefore you have even more separation from the observation error. So it's, some people take it as good, okay, because I don't know how to say that. Okay, for 3 significant figures, it seems to be like you have less error in conservative. Okay, so that's how they take it. So it's kind of a little bit weird in understanding, but you can go that way. So where considerations is the where has effects on the measurement, and always where is going to cause you problems, okay, because it's definitely giving you more errors in your measurement. So the where is small but measurable, and also you can misunderstand the where. So in a simple case where we measured an inside diameter and noted its maximum and minimum metal limits. So the difference between these limits is the tolerance zone again, and the wear allowance usually reduces this tolerance zone, okay? So because the wear is add up error, so therefore it reduces your tolerance zone. So here when you look at it, your minimum diameter is a whole, okay, minimum metal limit is right here, and then your tolerance zone is right there, okay. So the part is your part right there, and then the maximum diameter is right here. It's for minimum metal limit. So don't get confused, okay. All you have to remember is a shaded area right there, and that's your tolerance zone, okay. The wear is going to decrease that zone, okay. And you can get it with your common sense instead of looking on the drawing and get confused. And here, this is just a gauge on studying that measurement. This go is okay, and no go is not okay, okay. So here you can see your wear, little wear allowance. So if you trace this, you're gonna see it is eating up this tolerance zone area right there, okay. You should be able to look at the picture and understand where the space are going, okay. So from here to here is a little bit of area. So this area, if you apply it to a diameter, it's gonna take, you know, a small area right there on 2D, of course, 2D diameter, a little bit out of that tolerance zone shaded ring right there, okay. So that's what it's trying to tell you. Okay, so this is all for chapter 9 calibration.